Yes, hello everyone. To ask, do you have any questions about the last times, about the problems I've added? Ah, uh, okay, so then let us continue. Uh, so, the last time we computed Lagrange function of the wave equation, namely, so the equation was u pt minus u xx equals to some f of t and x. Well, let us say that it was yeah. So original equation this one, and if we put the delta function g to t minus gxx equals to delta of t, delta of x, then solution for this gain function with conditions that g of g of tx for t less than 0 is 0. So a solution of this equation was 1/2 of heaviside theta of maybe of t yeah, it is much easier way to write it. Yes, thank you. By the way, this can also be written as a theta function of t squared minus x squared. And we see that this means that it is Lorentz invariant, because this is a Laplacian in Minkowski space-time with this metric, right? And this is this Minkowski squared of a vector tx. So we see that it is invariant. So I forgot, times heaviside theta of t. So this function is non-zero in this domain. So it is x t right, and here it is 1/2, and 0 everywhere else. So if you have this again function, then we can write solution of this equation as u of t and x equals to integral from minus infinity to t g of t minus t prime. Well, we can well, first let us write this definition: x minus x prime f of x t dx dt, and if you now substitute well, 2 plus infinity originally, but since it vanishes, we get this integral to t, and we will have integral from minus infinity to t. Yeah, thank you. Yes, thank you. Yes. And x, so f of t prime, and well, the integral in x, integral um, from x x minus t minus t prime to x plus t minus t prime dt prime dx prime f of t prime x prime. So so it means that if we want to find a value of u in some point, so this is tx plane x t, we should take this cone, or yes, which goes to infinity, and integrate our function f over this cone. So this is what we have. We can also ask the following question. So at this moment we can solve this problem for without any initial conditions. We just need to say that this f is decaying at infinity, so that this integral makes sense. Okay. Yes, it should be here. Thank you. So, but now let us try to solve the following problem. Let us maybe forget about the right-hand side, because we already know how to solve this equation with the right-hand side. Let us ask what happens if we solve this original equation, but with initial conditions that u of t or u of 0 x equals to u 0 of x, u of ut of 0 x equals to u1. u0 of x, u0 of u1 of x. Yeah. And here we can use the same trick as for the heat equation. So there is another way to prove this formula, which I will show for the Laplace operator. But for now, we can just try to use the same trick. So here we see this right-hand side, which can be interpreted as a force applied to our oscillating string. So this U is profile of a string, and this force is an external force. So if you want to have an initial condition like U0 equals to 0, let's start with this case, and ut is something, then physically it can be interpreted that we kick this string with some force with a profile given by U1. So let us try to substitute, and here it is a little bit trickier, so I don't know how to formulate it physically, but it corresponds to some finite displacement of a string. So if you want to perform this finite displacement in the infinitely small time, probably it means that we should apply force proportional to the delta prime of t, and it is more or less clear, because if x of t is heaviside theta of t, then x to primes of t is equal to delta prime of t. So we see that this finite displacement can be achieved by this force. So let us just solve the following equation: u t minus uxx equals to u1 of x. Well, let us say that it is in delta of t plus epsilon plus u0 of x delta prime of t plus epsilon. Maybe this epsilon is not needed, but let us keep it make it a bit more rigorous. And now, so of course we can perform all this tricks with a weak form of equation, like we can multiply by some C infinity function with constant support, then integrate everything carefully. But as I showed on some of the lectures, it is more or less equivalent just to integrating the original equation in a small region around t equals to minus epsilon. So if we have this, then we can say that integral from minus 2 epsilon to 0 of u t t dt minus integral minus 2 epsilon to 0 uxx dt, maybe not from minus 2 epsilon, not to 0, but to some tau equals to what? It equals to u1 of x, right? So this tau is E1 of x heaviside theta of tau plus epsilon. Plus U0 of x heaviside theta of delta function of tau plus epsilon, right? So now we can say that this integral is something finite. So this integral is just u tau of tau, and the value of u on the lower limit is 0, just because those are our initial conditions. So we should also add initial conditions here, that u of minus 2 epsilon x equals to ut of minus 2 epsilon x equals to 0. So we add these initial conditions, which imply that this u is 0 for all negative values of t. So now we can integrate this this first part. We can also integrate the second part and write that it is something something of order t plus 2 epsilon, because u itself is a normal function. So this integral exists, and is of this order, and t will be tau will be small. And so what we have on the right hand side is this u1 of x here we said theta of tau plus epsilon plus u0 of x delta of t plus epsilon. And here so let us remember this formula and do the same trick again. Like integrate left hand side in tau in the same limits. So integral from minus 2 epsilon to tau. And maybe let us just write the answer, because we know what the integral of derivative is. So integrate from minus 2 epsilon to t. Now it is a free variable. Oh, sorry, it was tau in the upper integration limit. It is estimation of this integral. I'm saying that u is bounded for some fixed value of x, so it is bounded, and so this integral is a kind of maximum of u on this interval from minus to epsilon to tau times the length of the interval. So. So I'm saying that this to say that when epsilon goes to zero and tau is of order epsilon, this will go to zero as well. Hmm? No, it depends on x, but for a given x, it is bounded by like so. When tau plus to epsilon is small, then like mm, so. So this is of order tau plus 2 epsilon. When we send this to zero, it will behave. It will be of this order. Mhm. Is it clear? Sorry, I forgot to write here tau and x. So now integrate it once again. dt. So this will give a u of t and x, and this will equal to. So if you integrate this function again, it will be of order t plus 2 epsilon squared. So big big O plus integral of this one, which is of order t plus 2 epsilon. And finally, this last integral, plus u0 of x heaviside theta of t plus epsilon. So now let us compute this function at 0. So this u tau of tau and x equals to of 0 and x equals to it's here. So this delta function vanishes in this point, and this heaviside theta is 1. So it is u1 of x plus big O of 2 epsilon. U of 0 and x equals to big O of 2 into epsilon plus u0 of x. And now we send epsilon to 0 and get what we wanted. So initial conditions are correct, and then we have a solution of this equation for all bigger. Yes. So it shows that all the grand functions are actually related. Yeah, because if insert these initial conditions, then we get if we insert such rank inside, we will get these initial conditions. And now let us see what it means in practice. So what is the formula for this u? So u of t and x is equal to integral from minus infinity to plus infinity g of t prime x uh, g of t minus t prime x minus x prime, and here well, we can take this limit epsilon to 0 actually at this moment because because we are computing this u of tx for t greater than 0. So we can take the limit immediately. And it is u1 of x delta of t plus u0 of x and delta prime of t dt dt prime delta prime of t prime, sorry, and here of x prime dt prime dx prime. So the first integral can be computed explicitly as well as the second one. Ah, uh, no, this term is this one because it's an integral of something which is bounded, so it's a further t plus 2 epsilon. Yeah, you may multiply it by u1, but it is a further one. So, yes, of course. These functions do not depend on epsilon, and they're smooth. Well, not necessarily. There are some functions, but they don't depend on this epsilon. So, so there is only this essential term. So now, if we integrate this expression, we get the integral from minus infinity to plus infinity g of t x minus x prime u1 of x prime dx prime minus the integral of the same kind so it is derivative in t prime but no actually it will be with a plus sign because integral of delta prime of x, delta prime of t, f of t dt equals to minus f prime of 0. So it's derivative, it's minus derivative in t prime, which is the same as derivative in t. So it will be derivative of g of t x minus x prime u0 of x prime dx prime. So and you see that this formula actually works in arbitrary dimension. We only solved the time part of our equation. And so if we now use explicit formula for g, we can further rewrite this as integral from minus infinity to actually yes, from minus infinity to plus infinity. This Heaviside theta is non-zero only between x minus t and x plus t. So let us use this. So it is 1/2 integral from x minus t to x plus t u1 of x prime dx prime plus and here we need to compute the derivative of this grain function. So we can do this looking at this picture. So
Where did the minus from the data prime go?
it's just, in some sense, it can be understood as a definition of this generalized function, but
I just don't know where the minus went when we integrated. Like there's a plus.
yeah, but we differentiate it in t prime, which is with minus sign, and it is the same as minus derivative in t. Mhm. So it's so if you compute a derivative of this um, grain function, then what 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 do we get? So here it is 0, here it is 1/2, and time goes in this direction. So we can conclude that dt of mm, g of t and x is delta of 1/2 delta of t plus x on this half plus 1/2 delta of t minus x. Right? So just looking at this picture. So if you substitute it here, so if you now integrate this delta functions with u of u0 of x prime, we will get plus 1/2 u0 of x minus t plus u0 of x plus t. Right?
Why did x minus t and not t minus x?
Because there is x minus, well, let us maybe compute this explicitly. So its integral from minus infinity to plus infinity, 1/2 of delta of x prime. So delta function is symmetric, so we can write x minus x prime plus t plus delta of x minus x prime minus t u0 of x prime dx. So the first integral is the same. So in the first term, x prime should equal to x plus t. So it will give 1/2 of u0 of x plus t, and in the second term, x prime equals to x minus t. So it is u0 of x minus t. And actually, this this solution can be written in some other form. So if we introduce a function which is let us fix some point and integrate this u1 of x. So let us say that u 1 tilde of x equals to integrate from some point to x u1 of x prime dx. It's by definition. Then the solution can be written as 1/2 of u1 of u1 tilde of x plus t minus plus u0 of x plus t plus 1/2 minus u1 tilde of x minus t plus u0 of x plus t. So there of x minus t. So maybe it's this formula is kind of the most clear way to present a solution of this equation. Because we see explicitly that a general solution of this equation with some boundary conditions is given by a sum of functions of x plus t and x minus t. So in principle, we did not need to compute this gain function. We could just take this equation and solve it explicitly. Namely, so So if you introduce these variables xi plus minus, which equal x plus minus t, then d then dxi plus would equal to 1/2 of d dx plus dt. Well, we can just write like this. Dxi plus minus equals 1/2 dx plus plus minus dt. So and then if multiply dxi plus dxi minus, then of course we see, or maybe I should have chosen different order, but anyway, we see that it is 1/4 of minus 1/4 of dt squared minus dx squared. So and now so because of this our wave equation turns into dxi plus dxi minus u equals to 0. Therefore u of x and t, or of t and x, equals to some f plus of so what did we write there? It was x plus t, x minus t. So it is f plus of x plus t plus f minus of x minus t. Like this is precisely what we got starting from this story about the green function. So here is the solution, and if you want to impose some initial conditions, then then we can just solve a pair of equations, f plus of x plus f minus of x equals to u 0 of x, f plus prime of x minus f minus prime of x equals to u1 of x. And when we have this, we can integrate the second equation. So the first one is the same. And the second one is f plus of x minus f minus of x equals to, so I've introduced indefinite integral of u1 as u1 tilde, and let us use it here. So it is u1 tilde of x. So we see that it is actually not very well defined. It's defined up to a constant, but it's not a problem because these functions themselves, f plus and f minus, were defined up to addition of some constant and subtraction of the same constant from this function, because constant is both function of x plus t and x minus t. So that's not a problem. So we have this, and therefore f plus of x equals to u0 of x plus u1 tilde of x over 2, f minus of x equals to u0 of x minus u1 tilde of x over 2, and 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 therefore u of x and u of t and x is u0 of x plus t plus u0 of x no, plus u1 tilde of x plus t over 2 plus so u0 of x minus t minus u1 tilde of x minus t over 2. So that's all. So in principle, this blackboard is enough to derive a solution of this equation. And moreover, we see that in this way we obtain both of these green functions, like for the first derivative and for the function itself, and if we know this relation between between different green functions, we can also recover this solution for an homogeneous equation. But we can obtain this solution for an homogeneous equation by just solving this one. We can put here f of x and t, so we will just need to compute this integral carefully. So it's also not a big problem. But we were so lucky because it was a one-dimensional case, and because we could factorize this Laplace operator. So actually, this D'Alembert operator. But for Laplace operator, it works somewhat similar, but it is not so trivial, mostly because we can consider different initial and different boundary value problems. Here we are a little bit restricted because, for example, we cannot put some trivial boundaries and ask for for solution of the boundary value problem. So let me check the equation. So do you have any questions about this? So, and you see that although our original equation contains second derivatives of u, a solution of this equation contains only this function which initial values and integral of this function. So in principle, this solution, so this initial conditions can be, for example, discontinuous. Even this would be fine. They should not necessarily be differentiable, and this solution still exists. It still makes sense, and The meaning of this is that we could actually solve not this equation, but the weak form of it, where we multiply u by, where we multiply everything by some function phi, and move this derivatives to this function. So so for any phi in C infinity with compact support, for two this integral of phi tt minus phi xx times u of u dx and dt equals to integral so it's for f of x and t, and if you want to add initial conditions, then maybe we should be a little bit more careful. Let us be more careful. So if you want this equation with initial conditions, then what do we do? We integrate from 0 to t, and here from 0 to infinity dt from minus infinity to plus infinity in x, and we multiply this equation for x and t, u t minus u xx minus f. So we integrate by part and get first integral from minus infinity to plus infinity phi of x phi of tx, phi of tx ut of phi of 0x ut of 0x dx. Then if we integrate it by parts once again, we will get minus integral from minus infinity to plus infinity phi t of 0x u of 0x dx plus integral from minus infinity from 0 to infinity dt dx phi of integral. So we get this equation, and now we say that on this one is the initial condition u1 of x, this one is the initial condition u0 of x, and this equation should hold for any phi in C infinity with compact support of r greater or equal than 0 times r. So this solution actually solve this more general equation, where we don't need to ask this function to be even differentiable. So is it fine? Uh, Okay, and this simple form of solution allows us to solve this wave equation using only a pen and a piece of paper. So if someone brings you two initial conditions, u1 of x and u0 of x, you can draw them and then draw a solution for arbitrary time. So, namely, if u0 of if, for example, u1 of x is 0, then we can then we see that this u of t and x equals to 1/2 of u0 shifted forwards by time t and backwards by time t. So uh, so for example, when we have t equals to 0, and we get something like let us take a function of this shape. Let us say that there is triangular initial condition. Okay. For example, it is 1, it is -1, it is some again 1. So we imagine that it is actually a sum of similar triangles of height 1/2. And for example, what happens if so this is u and this is x? What happens if we draw this picture for t equals let us take t equals 1/2. So one triangle will be shifted by 1/2. 1/2. Another is shifted by -1/2. And so they will be smaller. So this triangle is here, So this is 3/2, and this triangle will be here. And this is minus 3/2. So we should take sum of these two functions, and so what is the value of this sum? So it equals to so we can check it in this point. So sum of these two linear functions will be constant. Uh, so and this constant equals to 1/2. So it's 1/2, and it spreads from 1/2 from minus 1/2 to 1/2. So it's constant, and then decays to 0 linearly, like this. So in this shape, and if we take some big T when they stop interacting, like T equals to 3, and then we will just have two triangles, one located at 3, is 3, 4, 2, and another located at minus 3. So then I think the idea should be clear, right? So if we have this, so it's simplest initial condition when we have a zero derivative. But if we have instead a zero value of function and some non-zero derivative, then we should take a difference of this u1 tilde and this u1 tilde. So if for example, we have mm, let us consider another example. If u1 of x is given by such function, like we keep a string with a unit force on the interval from -1 to 1. Then the integral of this u1 of x will be given by -1. Maybe let us put here 2, because I don't want this 1/2. So the integral is this one. If you integrate, or maybe no, it's fine. So it reaches point. No, maybe no. Let it be 1. So it reaches point 1 here, and goes further. So its limit and value is 2. So if we now want to compute u of t and x, let us compute it for some small time. So u u of maybe 1/2 and x. So so the first term in this formula is u tilde of x plus t. So it is shifted in the negative direction. So this point will be shifted to minus 3/2. And this will be with positive sign. So probably I'll need some free space here. And here it, no, sorry. Here it reaches 1/2. Here it's 1/2. And we subtract the same function shifted in the positive direction. It's 3/2. So if we now compute this difference, then we see that at this stage it is constant. At no, at this stage it's linear from -3/2 to -1/2. Then it becomes constant. Then it becomes linear again, and then it again becomes constant. And then it becomes 0. So this function is like this. And we see that if we further increase this time,
So the two waves does not separate, they do not split in scale.
yes, because when we take this infinite limit, we see that the value of function at 0 will equal to 2, no, to 1, actually. So no, the fronts of these two waves separate, so they move independently. But final value of u will be fixed because in principle there are infinitely many equilibria of a string. So if we put u equals to some other constant different from 0, it will still be equilibrium position of a string. So some physical intuition for this probably should be something like this. In this case, total momentum of a string is zero, because original original velocity was zero. So the number of points were like the measure of points where when u prime is 1 should equal to the measure of points when u prime is 0, and they appear on this left and right side of these triangles. And but here we give the string some initial momentum, and it should somehow be realized. So it comes from this from motion of this right front and the left front. So ut is positive here and here. So so we can actually it's not so much to tell about this equation because it is simple. So maybe the only problems we can solve is like we are given with some initial conditions. Draw some pictures for you of t. But by the way, we can a little bit complicate this problem by adding non-trivial boundary conditions. So maybe let us erase this. So so in principle we can consider different conditions, but the simplest ones are Dirichlet which is u of t0, like it's boundary condition for half string equals to 0, and it means so pictorially it means that this the string is fixed. So and another condition is a Neumann boundary condition. ux of t0 equals to 0. Uh, so a picture in this case is the following one. So we place some pole at point 0 and say that in the end of a string can slide here without any any friction. So like this. So if any force like so if this angle changes a little bit, then this ring immediately moves up or down, and so this angle so this derivative is always 0. Like this. Well, actually, we can also impose mixed boundary conditions. I don't know if they have any name, like ux plus let me think. Plus some well, alpha ux plus beta u equals to 0. So does anyone have any idea what this means physically? Uh, yes, so which physical system can realize this? So ux is remember when we derived equations of motion for this string, we told that it has some attention t, uh, uh, and this this force which equals to uxx appeared because when this string is not completely straight, then this attention does not compensate itself on the left and on the right. There is some angle. So but when we look at the endpoint of the string, then projection of this tension of this force of tension to the orthogonal line is proportional to the to derivative of u, and so what can we say about this equation? So this term is a force acting from this string. So, and this force is compensated by some other force, which is proportional to u of, sorry, it's t0, t0, u of t0 goes to 0. So I want to say that it means a similar picture. But there is some spring here. So that return force is proportional to u. So this is so this term corresponds to spring, and this term corresponds to force acting from the side of our string, because mm, this force this force is proportional to a t times ux. So those are physical boundary conditions, and they are distinguished by the fact that those are mechanical systems which kind of so they're kind of potential mechanical systems, so that we can assign some energy to this spring, and the energy of the spring and the string will be conserved. Because, for example, we can imagine some boundary condition which will contain viscous friction here. So we can, in principle, add here plus some gamma qt of t0. It's not prohibited, but well, and in principle, we can consider such systems. So the only problem is that it will eat the energy from a string. So
But this way is no longer is a boundary condition, but becomes another equation.
uh,
Because we have
no, why? Uh, if you ask how to solve this, I don't know immediately, but I think it should be compatible with the equation. No, let me think. Oh, I think it should be fine because we solve this equation uh, on the half line, and we have absolute freedom to do something on the left half line. So we should look for completion of the solution to the negative half line, so that this condition holds at 0. So it's not like a equation at this particular point. It's just a condition for you. So, but now how to solve this equation with this boundary conditions? So those are homogeneous boundary conditions, and we can also add here inhomogeneous conditions. So maybe let me write it from the very beginning. Maybe which letter to use? Maybe some V. V0 of t, V1 of t, some V2 of t. Well, of course, here as before, we can first solve equation for zero boundary condition and some trivial initial conditions and then add to it solution of this equation with non-zero boundary conditions and some trivial initial conditions. So we can start from solving this problem for v0 of t equals to 0. So u of t0 equals to 0. So and mm, and in principle we can solve this equation of t minus uxx equals to some f of xt. With some arbitrary force on the right hand side. And well, let us say that we compute the gain function from the very beginning. G of it's delta of x, delta of t, delta of x. And so this holds for x greater than 0. And it is quite easy to solve this equation using the following argument. So it is symmetric under u under x to minus x. So we can impose symmetry or anti-symmetry condition on our function u. So namely, we ask it to be so u of t minus x equal to minus u of t and x. So it's equation for the gain function. So if we impose this condition, then u of 0 is necessarily 0. And so we can imagine it in the following way, that we define some so and if we well I don't know, maybe it's better to write here some arbitrary no. So, and if you ask this, if you define u of negative x's in this way, then it means that we should define f of so if it is f of t and x, then it should be defined in the same way. F of t minus x equals to f of t and x minus f of t and x. So Practically, it means what? That if you want to solve this problem with, for example, this initial condition or with some non-trivial force, then we should add uh, the image of this initial condition or force on the negative half line, and when they start moving, then we will see the following picture, like so it will split. One piece goes here, one piece goes there, and uh, oh, sorry, like this. Uh, and and at some moment this triangle crosses zero and moves in the negative direction. So this goes in this direction, this goes in this direction. So they cross zero at the same time, and because it's a sum of opposite functions, then the value at zero is always zero, and as a result, we will have this picture. So we will have this triangle moving here, and this triangle moving here, and the image of this picture here. So so it means that the grain function on a half line for this case g. So for indirectly boundary conditions of x and t equals to g of x and t minus g of minus x t. And you see that we obviously have that g directly of 0 and t is always 0 because these two grand functions cancel. And it's also clear that this expression is a really grand function because oh, sorry. I wrote something stupid because in this case we don't have this symmetry of of x to minus x. No, we don't have shift symmetry, so so grand function of directly of x prime t equals to g of x plus x prime x minus x prime comma t minus g of x plus x prime comma t. Sorry. Hmm? What do you mean? Because before, so gain function was always a function of x and x prime. But in the previous cases, when we had strict symmetry, it depended only on the difference of x and x prime. And here it depends on both coordinates in this way. So it is g of x minus x prime and g of x plus x prime. So we can easily check that when x prime is 0, or when x is 0 as well. No, so let me think for a while. Hmm. So um, this gain function was symmetric in x minus x prime, right? G of x t was equal to g of minus x and t. So this directly of 0 x prime t equals to 0. And it solves this equation with delta functions in the right hand side because sorry, here I should have written g minus t prime x minus x prime. Yeah, sorry. Because again, there is no translation symmetry. So this gain function solves this equation because the Strauss gain function of x minus x prime has solves the equation with delta functions in the right hand side, and this second gain function gives a delta function somewhere for negative value of x, but we don't care because this equation should be satisfied only for positive values of x. So effectively it solves a homogeneous equation, and if you look at point x equals to 0, then we see that this gain function is 0, because original gain function was symmetric. It is g of minus x prime t minus g of plus x prime t, which coincide. And in the same way, we can write the formula for Neumann gain function. G Neumann of x and x prime t is g of x minus x prime t plus g of x plus x prime t. So dx of g Neumann of 0 x prime and t is equal to 0. So is it clear? Hmm? Because gain function is symmetric in x. So that picture somewhere, like it was given by this plot. So x and t. So it was symmetric, and its derivative is anti-symmetric. It's like x derivative. So this one also vanishes. So it means that we see a reflection of these waves at point 0, and for the clear boundary condition, this reflection it happens with a flip of phase, saying that we have a minus f after reflection. For Neumann boundary condition, it is with the same sign. So if it was Neumann boundary condition, then this triangle would be flipped. So is it fine? Uh, so what else do they want to tell? Ah, so one more thing. Let me think. Yeah, so one more problem which can also be solved by this method of images is a problem with time-dependent boundary conditions. So again, let us say that for x is greater than 0, we have this solution of equation here for u xx equals to 0, and u of 0 and t equals to some v0 of t. So does anyone have any idea how to solve this equation? Mm. Uh, mm, well, in principle, we can do this. This is how we will deal with Poisson equation. But here it suggests something simpler. By the way, we should also say that u of 0 and 0 and oh, sorry, it is t and 0. U of 0 and x should be 0. And also this 0 of 0 is 0, because otherwise it makes no sense. So here is just something simpler, because we know that solution of this equation is a sum of two functions, right? So if we have this equation in some domain, then we know that it is a sum of two functions. Hmm? It's a bit too much because if no, let me think. Maybe it's just fine. Say 0 of x plus t and 0. there is a problem. If you write something like this, then it will be non-zero for all possible values of x. Because we should also have initial conditions, like u of ut of 0 and x is equal to 0. So we have this boundary and initial conditions. So I'll propose the following picture. Suppose that we have some plot for v0 of t. So v0 of t, and it is t. Uh, so it is 0 at 0, and also for all negative t's. So it is some function, maybe negative sometimes. Uh, uh, so I propose to say that we just so no, how let me draw it some other way. Let's say that it is v0 of minus t. And let us imagine that we have the plot of this function down on the negative line, and the positive half of line is our string. So if you start to move this plot in this direction, then the value at 0 will be precisely what we want. So maybe. So if you imagine that we move it to the right and keep track of its value at 0. So we will precisely get all these values starting from the smaller ones to bigger ones, and so it will solve our boundary condition. And since it is a function which moves with speed 1, it will solve the wave equation. It will be a wave moving in the right direction. So of t minus x. So yes. So u of t and x equals v0 of t minus x. U, so we check that u of t and 0 is v0 of t. U of 0 and x is v0 of minus x, which is 0 because it is 0 for negative times. We start this problem, we solve this problem starting from t equals to 0. So v0 for of t less than 0 equals to 0. Also ut of 0 and x is v0 prime minus v0 prime of minus x. So it is simple. And so if you have a fixed
Is zero just zero? We can write v0 in as the sum of two functions, one of which is 0 before and what means 0 after that. And then we have
No, but what for? We solved this equation with some initial conditions at 0. So, in principle, we should not we should not know what is the value of this function for negative times. We just define it as 0. So. So it means that if you start to draw some if you start to move the left hand side of the string according to some law v0 of t, then we will see this precise function moving in the positive direction without changing its shape. So. So in the tells shall I tell so and oh, if you want to do the same for the for x derivative of u, then it can be solved precisely in the same way. We'll just need to integrate this function on the right hand side and substitute instead of v0. So it is an identical problem. So there is it's 1554. Maybe it's better not to start a new topic now. So. Probably I'll had some problem about this gain function, like how to derive these expressions using Fourier transformation. But it should be easy. But do you have any questions about all this? So next time I will tell a little bit more about this one-dimensional equation, and we will switch to a higher dimension. There's an interesting phenomenon which 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 is that this green function in even dimensions and in odd dimensions has is qualitatively different behavior. So here we had like both fronts of this wave, and in 2 dimensions we'll have only one front, and another front will turn into infinite tail. So okay, so thanks for your attention.